Hi everyone, this video covers some examples from the 1B homework. Let's get started. Just like in the 1A homework video, I'm going to be doing the view and example problems because those problems are very similar to the problems you'll all see in your homework, but they're not exact. So, alright. Determine whether the formula determines y as a function of x, if not, explain why. And these are given, it appears in the form of multiple choice. I'll do the view and example and I'll just try to predict what type of multiple choice questions you'll be receiving. Okay, so we have y equals the square root of x minus 11. A couple different ways you could figure this out. If you were to graph it, you would see that it passes the vertical line test. At no point are you going to get two y values for the same x value, so it is a function. Let's see. Oops. It's probably going to be something like this, so I'll write that out. Or I'll just write C. Okay, number 2. Same thing. In this case, In this case, the answer is going to be no because it does not pass the vertical line test. You know what? I'm just going to write yes or no instead of C or A or B because I'm not sure what it will be in each case. So this one's a yes, and this one's a no. I'm pretty sure the reasons are all very similar. It's just following the definition of a function. Yeah, as you can see, each x leads to a unique y, each x does not lead to a unique y. So yes or no. All right, number 3. Vertical line test, this does pass. And that's all they want. Number 4 does not pass. Or let me look at you an example. It does not pass either. No work to show, just look at the graph. Okay, find the domain of the rational expression. I'll write this down and then go back to the dot camera. We have f of x equals 2x minus 1 over x plus 5, x minus 4. Okay. So, this domain, what we need to do is we need to figure out where the denominator equals 0. Because the denominator cannot equal 0. So, this can't equal 0. So, x cannot equal negative 5 or positive 4. Which means the domain is going to be negative infinity to negative 5, not including 5, negative 5 to 4, and 4 to infinity. Basically everything except negative 5 and positive 4. All right. Okay, for number 6, we have the value, the square root of 7 minus x over x plus 3, x squared plus 1. Okay, so once again, our denominator cannot equal 0. So x cannot equal negative 3. This it can't equal 0 because once you square the x, you're going to get a positive number. Then if you add 1, you're going to get a positive number. So x cannot equal 3. And then whatever's in the square root must be greater than or equal to 0. So subtract 7 and then divide by negative. Anytime you multiply or divide by negative, you have to flip the sign. So x is less than or equal to 7, and it's not equal to negative 3. So the domain appears to be negative infinity to negative 3, not including negative 3, and then negative 3 to 7, including 7. All right. All right, number 7. Go on to another page. Okay, for number 7, we have f of x equals x squared over 12 minus x squared. Okay, so they don't want the domain this time. This time they want the range. So we're going to be using our graphing calculators. Alright, so we have x squared over 12 minus x squared graph. Alright, it appears to go from negative infinity, and I can't tell if this is 1 or 0. I'm going to use table. The way you access table is you hit second and then graph. And let's see here. It appears that it gets very close to negative 1. Sorry, I think I said positive 1. I meant to say negative 1. On the side gets very close to negative 1, but doesn't quite get there. Okay, so it looks like it goes all the way up to negative 1. So the range would be from negative infinity to negative 1, not including negative 1. Then there's a gap all the way up to 0. It does include 0, though, to infinity. All right. Number 8. Okay, identify local extrema and intervals of increasing, decreasing. Okay, so here we have, they don't give us the equation, they give us the graph. A local maximum is here, local minimum is here. This looks like a point of inflection. Okay, and they're giving us these points. Do they give you the points here? Okay, so they give you the points, you just have to determine is it a maximum or a minimum. Okay, so in our case, negative 6, negative 1 is clearly a maximum. And negative 2, negative 17 is clearly a minimum. Oh wait, no, sorry. Negative 2, negative 17 is clearly a point of inflection, but they don't ask for that, so it's neither. And then positive 2, negative 35 is a local minimum. So here's what I have on my paper. And then increasing, decreasing, I'm just going to real quick. Okay, it's multiple choice, so they would just want to know, you just need to select the correct interval. Actually, since we know these, we could probably, we're given these 3 points, we could use that to figure out the increasing, decreasing. It is increasing from negative infinity all the way to negative 6. Then between negative 6 and positive 2, it's decreasing. It's increasing again from positive 2 all the way to infinity. Okay, so increasing from negative infinity to negative 6, including negative 6, and from positive 2 to infinity. It is decreasing from negative 6 to positive 2. Okay. All right, graph the function and identify intervals where it's increasing, decreasing, or constant. This one is clearly decreasing from negative infinity to this point, constant here, and then increasing here. Do they give you the graph? Oh, you have to choose the correct graph. Okay. All right, so let's graph this. For number 9, we're given g of x equals the absolute value of x plus 6 plus the absolute value of x minus 4 minus 6. Once again, absolute value can be found under math and under number. It's the first one. X plus 6 plus x minus 4 minus 6. There we go. All right, so it actually looks pretty clear that it is 1, 2, 3, 4, 5, negative 6 and 4, and positive 4 and 4. If it wasn't clear, you could use trace and estimate. But this point, I'm pretty sure is negative 6, 4, and I'm pretty sure this point is positive 4, 4. And it appears that that's what it is here as well. All right, so is it multiple choice here as well? No, this one you have to fill in. Okay. So it is increasing from here to here, so positive 4 to infinity. It is decreasing from here to here, negative infinity to negative 6. And it is constant between the two. There you go. All right, number 10. Use a graph to define all local maxima and minima. Okay, so for number 10, we are given f of x equals negative 6 minus 4x plus x squared. Let's graph it. Negative 6 minus 4x plus x squared. Okay, it looks like we have one minimum down there. Second calc minimum is number 3. Left bound. Enter, right bound. Enter, guess, enter. Looks like the minimum is at 2, negative 10. And these are fill-in. Okay, so they want y equals at x equals. So there is a local min at y equals negative 10 at x equals 2. I think this one actually should be of. Let me see what they use. Oh, they don't use anything. I'm going to say of. And that's it. There is no local max. All right, let's take a look at number 11. Because there's no viewing example, I'll just do this one. If a function f is increasing for all real numbers, which of the following describes how f of x changes in tandem with x? Is x increases, f of x increases? Well, that is the definition of increasing. If x increases as f of x decreases, that would be decreasing. If it increases regardless, that doesn't make any sense. When x decreases, f of x increases, that's the same as b. So it must be A. And I'm going to go on to another page for number 12. All right. Determine the intervals on which this is concave up and the intervals where it is concave down. Identify all points of inflection. Okay, they are, oh, okay. Well, let's see what we get. So the graph of this is going to be we know it's concave down because it's a negative x squared. Oh, let me switch to my dot camera. As expected, concave down pretty much the whole interval. So it is concave down from negative infinity to infinity. At no point does it switch to concave up. Okay, let's go on to number 13. All right, this one's going to be a little more interesting. For this one, we have h of x equals 0.7x cubed minus 5. Let's graph this one. .7x cubed minus 5. Alright, so it is concave down and then switches to concave up, and it appears that the point of inflection is right there, which is x equals 0, y equals negative 5. Let's see what form they want it in. So they just want the points, okay. So it is concave up. from negative infinity to 0. Sorry, it changes concavity at 0. It is concave down from 0 to infinity. Okay, and point of inflection, or inflection point, would be 0, negative 5. All right. All right, moving on to number 14. Determine the intervals on which the graph of g of x equals 25 over x squared is concave up and the intervals on which the graph is concave down. Same thing as last problem. We'll write down this equation and then we'll graph it. So g of x equals 25 over x squared. Okay, it appears to be concave up from negative infinity to 0 and concave down from 0 to infinity. This appears to be a vertical asymptote, so the function is discontinuous at x equals 0, which means there is no point of inflection. So, concave up from negative infinity to 0. Concave down from 0 to infinity, points of inflection, none. All right, number 15. Okay, determine whether the function is bounded above, bounded below, or bounded on its domain. Let's graph it and see. Oh, I'll write down the equation first. All right, so 12 raised to the, oh, that's 10, 12, goodness, 12 raised to the x power, it's going to be bounded below. Yep. All right, number 16. Does it want? Okay, I was looking to see if they wanted the lower bound. They do not. All right, number 16, same thing. They want to know, is it bounded above, bounded below, or bounded? So this one is y equals the square root of 21 minus x squared. The graph is given, apparently. Oh, no, it's not. If you graph it on your calculator, you'll get this, and it's clearly bounded. Okay, number 17. Can a function with range 0 to infinity be bounded above? Justify your answer. Okay, so if the range has no upper limit, it goes all the way to infinity, it can't be bounded above. So you're going to look for whichever statement reflects that. Okay, in this case it's A, no, there are numbers in the range that are larger than any possible upper bound. No, there are numbers of the domain. So this one, it talks about the domain, so be very careful that you select the correct one. Okay, I'm going to go on to another page for number 18. Okay. Determine whether the following function is even, odd, or neither. Let's write it down. F of x equals 2x root 17 minus x squared. Okay. It's clear from the graph that this function is odd. All right. They're doing it algebraically, which you can do. I think if it's clear from the graph, there's no need to go through these steps. But you can. It's actually a good idea to go through these steps if you're not sure from the graph, if the graph looks a little iffy. All right, number 19, determine whether it's even, odd, or neither. In this case, we have f of x equals 2x to the 10th power minus 8x to the 6th power plus 11x. Let's graph it. 2x to the 10th power minus 8x to the 6th power plus 11x. Okay, this is clearly neither. There's no need to check algebraically. It's not even close to symmetrical. All right, let's go on to number 20. All right. For this one, we have f of x equals 2x cubed minus 3x. Let's graph it. 2x cubed minus 3x. This appears to be odd. All right, number 21. Graph the function and tell whether it has a point of discontinuity at x equals 0. If there is a discontinuity, tell if it is removable or non-removable. Okay, so for number 21, we have f of x equals 16 over x. We already know that there's going to be a point of discontinuity there because your denominator cannot equal 0. Let's see what kind it is. 16 over x. Looks like an infinite discontinuity. There's a vertical asymptote there. So let's see what form they want the answer in. Okay, so you select the graph, and then it's yes or no, and what kind it is. So you select the graph that looks like the one on your screen. You can adjust the window to make it look more like the ones, more like the options to verify. It is discontinuous, and it is non-removable. So, yes, there is an infinite discontinuity, which is non-removable. All right, number 22. Same thing. Graph the function, tell whether there's a point of discontinuity, etc. So 22, we have f of x equals the absolute value of 6x over x. All right. Math 1, absolute value, 6x over x. This appears to be a jump discontinuity, which is also non-removable. I should put that here just so that there's no confusion. Non-removable. So here, yes, there is a jump discontinuity at x equals 0, and that is non-removable. All right. Okay, number 23. Find all horizontal and vertical asymptotes. All right, so we're given f of x equals x plus 8 over 3 minus x. For vertical asymptotes, we're just looking at the denominator. The denominator can't equal 0. Where it does equal 0, there's your vertical asymptote. I'm going to subtract 3 and divide by -1, and I get x equals 3. So vertical asymptotes, x equals 3. The horizontal asymptotes you can find by graphing these. All right, there appears to be a horizontal asymptote at -1. There we go. Okay. You know what? They're actually using a different method to find the horizontal asymptote. So what they're doing is they are using something that is actually going to be taught in a future unit. Let me see if I can find it and put it on the screen. I'm going to pause the video here for a sec. All right, this is something that appears in your 3B notes, so a little ways away, but it turns out it's very useful now. If you have a rational function, so a function on top or a polynomial on top, polynomial on the bottom, where n is the degree of the top function and m is the degree of the bottom function, then if n is less than m, the horizontal asymptote is 0. If they're equal, you're going to look at the leading coefficient of the top and the bottom, and that is your horizontal asymptote. If n is bigger than m, then there is no horizontal asymptote. I'm going to make a mental note to go over this on the whiteboard so you can put it in the margins, because it turns out it's actually very useful for some of these problems. So in this case, because the degree on top and bottom are the same, we're going to be looking at the coefficients, the leading coefficients, which in this case are 1 and -1. 1 over -1 is -1, and that's how you know that the horizontal asymptote is -1. All right, let's go on to, let's see here. All right, number 24, I'm going to go on to another page. All right, use a method of your choice to find all the asymptotes. We have f of x equals 2x plus 2 over x cubed minus 729. All right, so x cubed minus 729. This is, I'm not sure if you went over the difference of cubes in Algebra 2. I'm actually going to write the equations for both the sum and difference of cubes. A cubed plus b cubed. If you need to factor that, it's a plus b. A squared minus ab plus b squared. A cubed minus b cubed is a minus b. A squared plus ab plus b squared. If it helps you to remember when you're adding, this first one is adding. When you're subtracting, this first one is subtracting. The second sign is going to be opposite, and the third sign will always be positive. So applying this rule to this here, the cube root of 729, let's see here, is 9. So we've got x minus 9 times x squared plus 9x plus 81. All right, so this can't equal 0, or that where this equals 0, those are our asymptotes. Clearly at x equals 9, this one we would probably want to use the quadratic formula, but let's graph it and see if there are any asymptotes. So we have 2x plus, parentheses, 2x plus 2, x cubed minus 729. Let's see here. Okay, so clearly there's an asymptote, a vertical asymptote at x equals 9. That appears to be the only one. If I'm just going to do a quick check. If we were to do negative b plus minus the square root of b squared minus 4 times a times c. All right. Without even solving, I can tell I'm going to get a negative number in the square root, so this is going to be our only vertical asymptote. And because the degree of my denominator is bigger than the degree of my numerator, I know my horizontal asymptote is going to be y equals 0. So vertical asymptote, x equals 9, horizontal asymptote, y equals 0. And you can also see from the graph, it's clear that it approaches 0 but never quite gets there. Okay, and finally, number 25. Match the function with the corresponding graph by end behavior and asymptotes. Okay, so number 25, we have f of x equals, view an example. F of x equals x plus 4 over 8x squared plus 1. Okay, I can't stop you from using a calculator on this one, but this one is designed to be done without a calculator. What they want you to do is they want you to figure out what the horizontal asymptotes are algebraically, figure out what the vertical asymptotes are, if any. In this case, there aren't any. And then use that to identify the graph. In this case, so I'm just going to find the vertical and horizontal asymptotes, and then we'll figure out by process of elimination. There are no vertical asymptotes because x squared plus 1 doesn't ever equal 0, so vertical asymptotes None. The degree of the bottom is bigger than the degree of the top, so horizontal asymptotes would be y equals 0. So let's take a look here. There are no vertical asymptotes, so it has to be one of these two. And horizontal asymptote of y equals 0, so it has to be this one here. There we go. I think that was C. All right, and that's the end of the 1B homework example problems. Thank you so much for watching.